Okay, so today we're going to do some more solving trigonometric equations. So the focus for today is going to be some more advanced examples of trigonometric equations. Before we begin, I'll just remind you of some of the factoring techniques that we'll need to know for this. These factoring techniques are like the sum product rule and the adapted sum product rule, those sort of things. Now, I want you to remember that the entire point of solving trigonometric equations is to find the value or values of an angle that would make the equation true. Oftentimes, you're given a specific domain, so in other words, a whole bunch of possible angles to work within. Just pay attention to that really closely. And just another reminder, we are using the note booklet, so you can follow along if you wish. So on page 35, some factoring review. Recall, factor the following quadratic equations and solve for x. So this first one here on the left, x squared plus 5x plus 4, that's a very classic sum product rule kind of question. So how we deal with this is the number attached to the x is your sum, and the number on its own is your product. So we're looking for two numbers that have a sum of 5 and a product of 4. And usually I look at my product first and go, okay, what two numbers would multiply together to give me that? Well, I think this one's not too bad. It's just going to be 4 and 1. Now, the nice thing about the sum product rule is when you don't have a number in front of your x squared, as soon as you identify the two numbers that give you a sum of 5 and a product of 4, you can actually jump straight to the answer. So again, those two numbers that add to 5 and multiply to be 4 are 1 and 4, because 1 plus 4 is 5, 1 times 4 is 4. So this actually becomes x plus 1 times x plus 4 equals 0. And that's all we have to do on this one, because it just says factor it. Oh, wait, never mind. It totally does say solve for x. There you go. I just ate my words. So now we have to solve for x. To solve for x, of course, we're going to wonder what values of x would make this statement true. The whole reason we factored in the first place was so that we could see something times something equals 0. Well, the only way that something times something could equal 0 is if either this piece equals 0 or if this piece equals 0. Well, we'll start with this one here. So x plus 1, if that equals 0, then x would have to be equal to negative 1. So there's one of our solutions. And then as for the other one, x plus 4 equals 0, well, then x would have to equal negative 4. So our answers on the first one here are x is negative 1 and x is negative 4. As for this next one here, there's a couple different ways you could do this. You could get x squared all by itself and then square root both sides, which works just fine. But what I'm going to do on this one is I'm actually going to notice this is a difference of squares. There we go. A difference of squares basically is just when you have something you can square root minus something else that you can square root. And we can square root x squared, no problem, and we can also square root 1, no problem. So this is a difference, because there's a subtraction here, of squares. So to deal with this, a difference of squares, square root each piece and multiply it by the other's conjugate. Okay, and by what I mean by that, of course, is if we square root x squared, we're going to get x minus square root of 1 is just 1. And then multiply by the conjugate, so the same thing all over again, except it's going to be x plus 1. And if you don't believe me that this works, you're totally free to multiply this back through and check that it does equal what you had started with. I can let you try that on your own time. I'm not going to waste your time right now, but bottom line is it's the same as before. Look at where each of your factors would make this equal to 0. So x minus 1, well, that'll equal 0 when x equals 1. And x plus 1 will equal 0 if x equals negative 1. So your answer there is x is plus or minus 1, basically. All right, next one, still on page 35, 4x squared equals 9. This one's going to be a little bit more challenging. Of course, there's no clear difference of squares here. I mean, you could subtract 9 on both sides, and then you might have a difference of squares going on. I'm going to tackle this one a bit of a different way, though. What I'll do is I'll divide by 4 on both sides. That's going to give me x squared equals 9 over 4. And then I'll square root both sides of the equation. This will give me x equals the square root of 9 over 4. Remember, when you're square rooting a fraction, you can just square root the top and square root the bottom. This actually works quite nicely, because if you square root the top, you get 3, and if you square root the bottom, you get 2. But just keep in mind, when you square root a number, you can actually get the positive or the negative of that number. So not only do we have x equals 3 over 2, we also have to keep in mind that this could be x equals negative 3 over 2. Because again, when you square root something, it could be plus or minus that answer. Okay, for this last one here, there's a number in front of our x squared, so we can't use the normal old sum product rule. We have to use something that I always call the adapted sum product rule. I don't know if it has a different name than that. That's just what I've always called it. The adapted sum product rule says that your sum is still the same. So you're looking for two numbers with a sum here of 7. but your product needs to be this first number times by this number here. So 2 times 3, you're looking for a product of 6. So let's ask ourselves, what two numbers would add together to give us 7, but would multiply together to give us positive 6? Well, those two numbers, of course, would be 6 and 1. Now, unlike before, we can't jump straight to an answer. We actually have to use these two numbers to break apart this middle term. So this is going to become 2x squared plus 6x, that's where I'm using this 6 here, plus 1x, and then plus 3 equals 0. So now what I do with this is I look at my first two terms and my last two terms, and I actually put brackets around them. I make sure that whatever plus or minus sign is in here is not caught up in any of the brackets. I do that on purpose because if this was a minus sign, as soon as we put brackets around these last two terms, we would have to change the sign of this here too, which is just part of the whole process. Anyway, from these first two numbers, let's think about what we could factor out of this. We could factor out a 2x. So if I take out a 2x from that, we're left with x plus 3. Plus, if you look at these two, it doesn't look like anything can come out of there, but when nothing can come out of there, I just take out a 1. So plus 1 times x plus 3. And then you know you've done this right when the stuff left in brackets is the same on both pieces. There's an x plus 3 here and an x plus 3 here. So this becomes 2x plus 1, so the stuff on the outside of the brackets, times by x plus 3 equals 0. Now look at where each piece is going to equal 0. This first one, of course, if you set this equal to 0, you'd minus 1 and then divide by 2 on both sides. So x is negative 1/2. And then on this one here, we would just say this is equal to 0. So move the 3 over and you have x equals negative 3. So those would be our two answers there. Now this stuff that I've just reminded you of, I know it took like 6 or 7 minutes of our time, but it's really important because we're going to actually have to use this today. So let's apply this to trigonometry. This is a question on page 36. Factor and solve the following trig equations. Tan squared theta minus 4 tan theta plus 3 equals 0 within this domain. Now, just at first glance here, this looks like absolutely nuts, but if you think about the basic form of this formula, it's like the sum product ones, where it was something squared minus something times something plus a number equals 0, right? So what I usually do is I make my life easier here by saying, let's say x equals tan theta. Now I can rewrite this whole formula by saying it's x squared minus 4x plus 3. All I've done is I've replaced the tan theta with an x, right? And then it becomes a little bit more familiar looking to me. This now looks like a normal sum product rule question, two numbers with a sum of -4 and a product of +3. Well, that'll be -3 and -1. So we'll go x minus 3 times x minus 1 equals 0. So then this means either x equals 3 or x equals 1. Now, as nice as it would be to just leave that there, we can't actually just do that because remember, x is tan theta. But from here, we can actually say, let's say for x equals 3, that we understand that tan theta therefore needs to equal 3. And for the other one, x is 1, tan theta needs to equal 1. Now, notice this domain here. This is actually quite important. This is just saying that our angle has to be given in radians, first of all, because it's based around 2 pi. But also, yeah, of course, it's in radians, so we gotta make sure we don't give a degree as an answer, right? Another thing just to keep in mind here is it didn't say anything in this question about exact values, so we don't really have to worry about that if we aren't asked for it. So what I'm trying to get at here is you don't have to worry about having, exact values. You can just have an approximate value here. Long story short, what I'm trying to spit out is just use inverse tan on this, right? But make sure, of course, because this needs to be in radians, make sure your calculator before you do any of this is in radian mode. So I'm just going to change my calculator to radian mode real quick here. And I'm going to take the inverse tan, so the inverse tan of 3. And what that's going to give me is theta equals, and I'll just round to the nearest hundredth because it doesn't say otherwise, 1.25. Now that's not 1.25 degrees, that's 1.25 radians, okay? So that's something very important just to keep in mind. Now, the other thing I want to keep in mind with this is this amount that I got here is a radian amount that's actually in quadrant number 1. Now the reason I know this is when you use inverse trig on a positive number, it always spits out an angle that's in quadrant 1 for you, right? Now quadrant 1, when it comes to radians, is between 0 and pi over 2. And pi over 2, I don't know the number off the top of my head. Because pi is about 3.14, we can estimate pi over 2 to be like 1.56, I think. So this certainly is within quadrant 1. But keep in mind, because tan is a positive number, tan by the cast rule could either be in quadrant 1, but it could also be in quadrant 3. So this is one of our answers, but this is just a quadrant 1 answer. We also could be in quadrant 3. And of course, if we're in quadrant 3, we have to consider this 1.25 a reference angle. So let's take our reference angle of 1.25 and add it to the full 180 degrees, or in other words, the full pi, right? So for quadrant 3, we're going to have pi plus 1.25. And pi plus 1.25 gives us approximately 4.39 is our angle. And of course, that's our angle in quadrant 3. Let's do the same thing with tan theta equals 1. If we take the inverse tan of 1, that is going to give us, just hold on, the inverse tan of 1 is, let's just say to the nearest hundredth, 0.79. So 0.79, that would be our angle in quadrant 1. And of course, because that's in quadrant 1 and we realize that tan here is a positive number, we could also be in quadrant 3 based on the cast rule. So we need to find for our other angle, pi plus 0.79, which gives us our other angle as being about 3.93. And that, of course, is your angle in quadrant 3. Anyway, let's move on. Let's try a different one. So 2 sine squared theta equals 1. This time we have our domain, so our possible angles being in degrees, and we're anywhere between 0 and 360, which is a nice normal domain for us. Let's try to solve for this. Let's get the sine squared all by itself. So let's divide by 2 on both sides. So sine squared theta equals 1/2. Then let's square root both sides. If you square root both sides, you're going to get sine theta equals plus or minus, because we're square rooting this. The square root of 1 is just 1. Square root of 2 is root 2. Now, hopefully this looks pretty familiar to us, and I won't blame you if you don't. 1 over root 2 is more commonly written, at least in this course, as being plus or minus root 2 over 2. Well, that's part of special triangles, right? That's, one of our special triangles, and it's actually our 45-degree triangle, right? So if you drew a 45, 45, 90 triangle, like so, you're going to see that the side lengths on here are root 2 over 2, root 2 over 2, and 1. Since we're saying that sine is either plus or minus root 2 over 2, well, sine, of course, is opposite over hypotenuse, so regardless of whether you look at one of these two angles, you're going to see that your theta, of course, is 45 degrees. But because it could be positive or negative, if you think of the cast rule, sine is positive in these two quadrants, but sine is negative in these two quadrants. So in other words, because sine theta is plus or minus the square root of 2 over 2, we could be in literally any of these quadrants. 45 degrees, clearly, is our answer in quadrant 1. But let's think about what our other quadrants would be as well. If we were in quadrant 2, we just have to take 45 degrees away from 180. So if we go 180 minus 45, that gives us 135 degrees as being our angle in quadrant 2. In quadrant 3, we would just have to add 45 degrees to 180. So 180 plus 45 degrees gives us 220, what am I doing here? 225 degrees is what we got in quadrant 3. And then if you're in quadrant 4, we just have to take 45 degrees away from 360. So 360 minus 45, which should give us 315 degrees. Good. All right, that one wasn't quite so bad, hopefully. Next one, oh boy, cosecant. Geez Louise. All right, so cosecant, this is going to be a little bit more of a trouble, but notice it's kind of like the first one we did with tan. It looks kind of like an x squared kind of equation. Now, this right here is what's really going to throw us through a loop. It says theta must be an element of the real numbers. That basically just means we have to apply a general solution, which is something that I talked about in the previous lesson. General solution is just like all your possible answers. We'll worry about that at the very end here. We'll just first start by worrying about our possible answers. Anyway, so what I would do is I would instead change this so that x equals cosecant of theta. So then this becomes x squared minus 3x minus 10 equals 0. This, hopefully you breathe a sigh of relief because that's more just a normal sum product rule question. We're looking for two numbers with the sum of -5, but a product of -10. Well, those two numbers are going to be x minus 5 times x plus 2, because -5 plus 2 is -3, and -5 times 2 is -10. Now that it's written like this, unfortunately, we can do this one of two ways. I'll just say x equals 5 and x equals -2. But really what each of these mean is cosecant theta equals 5. And I should have room if I do it over here. Cosecant theta equals -2. Now cosecant is one of our reciprocal ratios, and it's just a nightmare. They're awful to work with. So instead, let's change this to its actual primary trig ratio. Well, cosecant is the reciprocal of sine. So if we flip this around, we can say sine theta equals the reciprocal of 5, which is 1/5. And likewise over here, we can say sine theta equals the reciprocal of -2, which is -1/2. Okay? This one we'll do first, just because I think it's honestly a little bit more challenging. 1/5 is not something that shows up on any of our special triangles. That's just totally, out of left field, right? And if we think of our cast rule here, since it's positive, we know we have to be in these two quadrants. Well, if we take the inverse sine of 1/5, you're actually going to get your angle to be 11.5 degrees if you're in degree mode. If you're in radian mode, that's fine too, because this didn't say one way or another. It just said theta has to be a real number. I'm going to deal with degrees because I think degrees are just easier to work with. But this is your angle, of course, in quadrant 1. We've realized also that this could be in quadrant 2 because sine is positive here. So if we take this 11.5 degrees and take it away from our 180, that'll give us our angle in quadrant 2 as well. So theta could also equal 180 minus 11.5, which is 168.5 degrees. And that, of course, is in quadrant 2. Looking now at this other one here, sine theta equals -1/2. You could use inverse trig on this. There's nothing wrong with that. Or you could recognize that 1/2 is part of your special triangles. If you remember this side being 1/2, that means your angle across them is 30 degrees, which means this is √3/2, and this side is 1, and a 60 degree up in the corner. Sine being 30 degrees, or sorry, sine of theta is 1/2/1, so sine is 1/2. In other words, that means our angle must be 30 degrees. That's what I'm trying to spit out here. But since it's -1/2, that means we have to be down in these two quadrants here. So I can say that theta r, my reference angle, is 30 degrees. We're either in quadrant 3 or quadrant 4. If we're in quadrant 3, we have to add 30 degrees to 180, so it'd be 210 degrees. But if we're in quadrant 4, we'd have to take 30 degrees away from the full 360, so we'd have to come down this way to get 330 degrees. Whew, okay, we're not quite done yet though. Remember what I said at the beginning, we need a general solution for all of this. Honestly, to write a general solution, don't freak out about it too much. You just take each of your answers that you got and add 360 times n to each one of them. So here's what I'll do. I'll write out all my answers again. I'll say our general solution would be 11.5 degrees plus 360 times n, where n is an element of the integers. This basically just means, in plain English, 11.5 degrees is your answer, plus any multiple of 360 degrees from then on. So either adding or subtracting, because we're going n is an element of your integers, and integers are positive or negative whole numbers, right? Do the same for your others. 168.5 plus 360n, where n is an element of your integers. Follow it through, 210 plus 360n, where n is an element of your integers, and then of course 330 plus 360n, once again where n is an element of your integers. That right there, that whole clump of numbers right there, that is actually your final answer because it's expressed as a general solution. Whew, okay, moving on. So this next one is on page 37. Solve the following equations, okay, over the domain -90 to 270. This domain is just garbage. Like, what a stupid domain to have, but it is the question. We have to be mindful of it. That's fine. Notice -90 degrees would be if you just went clockwise down here. So this is like -90. And +270 is if you go all the way around and then you come over here, so +270. So this is just another way of dealing with all four quadrants. They just, for whatever reason, wanted to call this quadrant 4 from 0 to -90 degrees. It's dumb, I know, but that's what the question is. Let's just worry about that later. This question you can do in a couple different ways. This might look a bit challenging because there's cosine and sine in here. And I don't blame you for thinking that. But here's how I would personally go about this. I think in my answer key I did it a bit of a different way, but I like this new way a little bit better. What I would do is I would actually start by factoring out a cosine. Notice cosine can come out of this, and it can also come out of this. So let's do that. Cosine theta has been factored out, so that leaves 2 sine theta minus, if we take a cosine out of here, we just have 1 equals 0. Notice just in one step there, technically we now have the factored formula. So either cosine theta equals 0, as it would be here, or sine theta equals, if this was all equal to 0, we'd add 1 divided by 2, so sine theta equals positive 1/2. Well, we need to think about where cosine theta equals 0, and if you're ever not really sure, you can always use your graphing calculator, take the inverse cosine of 0. You have to be in degree mode, of course, for that. But you're going to find, long story short, that cosine is 0 when theta equals 90 degrees. But it could also equal 0 when theta equals 270 degrees. And again, this could also come out of the realization that cosine is really your x value, and where x is 0, because cosine theta equals 0, so therefore x equals 0, well, that'd be at 90 degrees and 270 degrees, right? So those are going to be some of our angles here. Just bear with me for a moment. I'll come back to this in a second because there's one other thing I got to tell you about this. But sine theta is 1/2. Hopefully you remember from several of the questions we've done that this gives us a reference angle of 30 degrees. But sine being a positive number from the cast rule tells us that we're either in quadrant 1 or quadrant 2. Well, 30 degrees is an answer in quadrant 1, so we're good there. And in quadrant 2, we would just have to take 30 degrees away from 180. So 180 minus 30, of course, gives us 150 degrees. So that would be our other one from that. Now, the last thing I got to do here, and this is what I was just alluding to a second ago, was we got to make sure that all these numbers kind of jive with our domain here. Well, 30 degrees certainly is within this. This is good. 150 degrees is also within this. So that's good. 90 degrees that we got right here is also in there. So it's good. But 270 degrees, you got to be careful. 270 degrees is actually not in this domain, because notice this part right here is just saying theta is less than 270, not equal to it. But notice on the bottom end of this domain, we had negative 90 degrees. Negative 90 degrees is, as we determined before we even started, the same thing as 270. And notice this sign right here is including negative 90 degrees. So instead of saying theta equals 270, I'm going to switch that down and put it into the really dumb domain we were given and say that theta actually needs to equal negative 90 degrees. And that right there would be our other answer. So the stuff that I put these boxes around, those would be the solutions to this equation. Let's do, I think, just a couple more. Yes. Oh, actually, no, this is just the last one, actually. And I chose this one because it's a weird one. I don't think I've mentioned it so far in this video, but hopefully you figured it out if you're following the booklet. I totally am jumping around this booklet. I'm not doing every single question in there because otherwise it would take forever, and I try to keep these under 30 minutes. But anyway, I digress. We're on page 38. This is a very, very bizarre question that we have in front of us. Solve the following equation over the domain 0 to 2 pi. This is another really normal domain. It's just in radians, which I know some of you probably don't like too well. How I would go about solving this one is get everything to one side. So 4 tan squared theta, we'll add 5 tan theta to the other side, so plus 5 tan theta, and then we'll minus this 2 over. So minus 2 equals 0. So then you might think, oh, okay, well, we'll just do the thing where we say tan theta equals x. So then we could say this is 4x squared because it was tan squared theta. 4x squared plus 5x minus 2 equals 0. And then you go, oh darn, well, this is going to be one of those adapted sum product rule questions. So we have to go, all right, what two numbers have a sum of 5 and a product of 4 times negative 2, which is negative 8. Well, save you the time here. You could sit here and like think about what two numbers would add to this and multiply to this. You're actually going to find that nothing does that. So now you're left with a choice. You can do one of two things here. You can either go, all right, first thing you could do is you could try using the good old quadratic formula. Now the quadratic formula is on your formula sheet. It's that absolute big beefcake thing in the top left-hand corner. You would have covered it back in Math 20. It says x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a, where this is your a, this is your b, and this is your c, the negative 2 being c, right? You could throw those in and find the values of your x's. Notice there'd be two values of x because you have to do the plus and you have to do the minus for this, right? So you have to do it twice, in other words. Yeah, that's one way of doing it. But the other way of doing this, because the question does not say anything about doing it algebraically, is you could just cheat and use your graphing calculator, which is exactly what I'm going to do for the sake of saving some time here. Plus, it's a lot easier. Now, just to let you know, I've already solved this in a graphing calculator. So before I actually do any of this, let me just show you what it's going to look like when you plug it into a graphing calculator. You're actually going to want to take advantage of this form right here, because when you have this equal to 0, this means you're looking for your x-intercepts, right? Your x-intercepts are where y equals 0. So where this whole thing equals 0, when you plug that whole side into a graphing calculator, what it means to equal 0 is y is equal to 0. So what I've done, I'll just switch slides here real quick, is I've actually put this in a graphing calculator. And how it would look when you plug it into y equals is this right here, 4 tan x squared. Notice even though in the formula we put the squared next to tan, you can't do that in your graphing calculator. You just have to say it's tan x squared. And remember, I'm using x instead of theta because there isn't a theta button in your calculator for some reason. Anyway, plus 5 times tan x minus 2. So we're looking for where this whole thing equals 0. So in other words, we're looking for where y equals 0. Now, before I did this, I also decided to change my window, and that's super important. Notice that theta is what you're plugging into this question, right? It has to be x again in your calculator. X is theta in this case, just because there's not a theta button, but hopefully you get the idea. Since this is your domain, set your window to match that domain. So in other words, the lowest x that I have in there, my x min, is 0. That's my x min. My highest x that I have in there, my x max, is going to be 2 pi. And you literally can put pi in your window up there. Like, that's totally fine. I think as soon as you move your cursor away, it actually calculates that to be like the 6.28 whatever, right? But I just took the screenshot when it said 2 pi, right? As for your x scale, I guess technically I could have set my x scale to something kind of like pi over 2 or something like that, but we really don't care. Because again, we're just looking for our x-intercepts, so I really didn't care to do that, so I just left it at 1, right? As for my y-min and my y-max, those don't really matter either. The only thing that matters is that you have to have y equals 0 somewhere in between these, right? And of course it is, between -10 and +10, it totally is. Long story short, where I actually graphed it, this is what the graph looked like given this equation and this window, right? Notice again, we're looking for our x-intercepts. So just visually on this, here's one, here's another, there's another, and there's another. Now, logically, there's probably going to be another one right after this, but because I set my window to be between 2 pi and 0, those 4 dots are the only ones that we care about. Now, again, to calculate these, you have to press second and then trace, this button right here, and then find where it says 2, 0. 0 is another way of saying an x-intercept, right? Then you have to manually find all 4 of these. Hopefully it's not a big deal for you guys because we've been doing it since about grade 10, but make sure you find the zeros using that way. Long story short, I actually have the answers written down just over here. Long story short, the answers that I got are x, or rather I guess I should say theta, because these are all angles as radians, right? Oh, and really, I really should have mentioned as well, my mistake, my calculator was in radian mode during all this. That is super important for you to understand. Needed to be in radian mode. Good thing I remember that. I almost totally forgot. Anyway, theta in radians, I got theta equals 0.31. I got theta equals 2.14. Excuse me, I just sneezed. Then I got theta equals 3.45. And then I got theta equals 5.28. And I guess setting my x scale to be 1 each time kind of helps us see that, although maybe not actually. That's quite interesting. Whatever. You know what? You get the same idea one way or another. I must be missing something. 3 point. Oh, I see. It's probably because there's a point right here that I just don't see. Maybe if I erase all this. Oh, it is. Good. Whew. I just almost had like a mini heart attack right there. Okay, good. So just repeating it again, these were your four answers that we got. 0.31's there. Notice it's between 0 and 1. Between 1 and 2, there's nothing. But then right over 2 at 2.14, there's your next one. There we go. Whew. Like I seriously almost had a heart attack there. There's x is 3, x is 4, right in between at x is 3.5. You have your next one. Between 4 and 5, there's nothing. And then between 5 and 6, there's another one. Whew, good. Awesome. That worked like a charm. So in other words, those would be your four answers, all of which are, of course, in radians. All right, so I've kind of pushed the time here. We're like at 30 minutes already. So for practice, do the questions that I've listed on here. That's it for chapter 4. Finally, this is a long chapter. We're all done. Just to let you know, the chapter 4 quiz is on Wednesday. That's Wednesday, April 8th, I believe. But I will open it Tuesday morning. For those that want to complete it early. You are under no obligation to complete it Tuesday morning by any means, but I have it open for 2 days because I think that provides a more flexible window. Now, Tuesday's lesson is going to be a straight to the point review of everything in chapter 4. I'll tell you exactly what you need to know for that quiz that opens on Tuesday and that I expect to be done on Wednesday. And also, it won't rely on the notebooklet. In case you haven't already been able to tell, I don't like these notebooklets. I'm like straight up, genuine, honest. Some of these questions are just garbage, but they are very useful and they are a great way of dealing with this, especially with this whole situation. Anyway, as always, if you have any questions, please let me know. Talk to you soon.